Hi. We're now going to figure out for a set of years, given as any type of array, which years are leap years and which years are not. The leap year rules are quite involved. The rules are like this. Every fourth year is a leap year, except every 100th year, which, even though it's divisible by 4, is not a leap year. Except if it's also divisible by 400, then even though we just said that then it wouldn't be, because 400, if divisible by 400, it's also divisible by 100, then it wouldn't be a leap year, then it is a leap year nevertheless. So it's an exception to exception rule. So we say every fourth year, and then every 100th year, and then every 400th year. What we want to know is the current year number that we're dealing with divisible by these numbers here. We don't have an is divisible by function in APL, but we do have a division remainder function. And if there is no remainder when you divide, then it's divisible. So let's take year 2000, for example. That was a very special one. We can see that it has no remainder for any of these. And if we take year 1900, then it was divisible by 104, but it wasn't divisible by 400. And if we say 1904, then it was only divisible by 4, but not by the two larger numbers. And 1905, of course, was not divisible by any of these numbers. Okay, so what we want to do here is compare with 0. 0 means that there's no remainder, and therefore it is divisible. And the rule is that if we have a 1 here, then it is a leap year. If we have a 1 here, then it's not a leap year unless we also have a 1 here. So it's a kind of yes, no, yes thing. And that can actually be expressed quite neatly using an XOR, which just means this one is true or that one true, but not both of them. So if we think about inserting a different from, that's what XOR would be represented as in APL, then we start from right to left and say, well, we have this one, but only if this one is false. If they're both true, then it becomes false again. And then we continue here. This has to have been true, but only if not this one. It has to be different from that. So that gives us that every time we proceed one step to the left, it's another flip as but not if that one. And that gives us exactly the exception rule. So we can do an XOR reduction that just inserts this different from inside the vector. And we can see that this says that 1905 is not a leap year, 1904 is a leap year, 1900 not a leap year, and 2000 is a leap year. So this really solves the problem for a single number, but we are told that we should handle any array. So let's modify this a bit. We'll start over here, and we're going to have an array of these numbers. 1905, we also had 1900 and 1904, right there. And conveniently, let's make them into a matrix. So this is going to be our argument. And we want each of these to be paired up with each one of these, no matter what the shape is over here. That calls for an outer product. So dot vertical style, that's an outer product, which combines the x's here, there's one axis, with the x's over here, two x's, and that gives us a three-dimensional array like that. We can see the layers here. So this is for the first one, and so this are the remainders for 400 with each one of these. So this the entire layer, it corresponds to this matrix that we have over here for 400 and for 100 and for 4. That means correspondingly that which are the numbers that correspond to 1900? That's the top left corner of every matrix. So the 300 and the 0 and the 0. And for the 1904, it's the one in the top right corner of each one. And in order to do our XOR reduction, we need to go down through the layers. So that's along the first axis. The first axis enumerates the layers. So we want to go through the layers here. That means we need to switch our slash, which was the last axis reduction, to a slash bar, which is first axis reduction. That gives us a matrix, just like this matrix over here, saying which years are leap years. Now we all just need to make this into a, sorry, this is wrong. We're missing the 0 equal there. There we go. This gives us an expression, but we need to change it into a function. We can easily make this tacit just by adding a right tag here, and then we can add parentheses around it, or we could have added an omega and braces. Either way, this tells us that the two right column ones, that's 1904 and 2000, those are leap years, but the two left column ones, 1900 and 1905, are not leap years. We could actually be even more clever. We've got here a scalar comparison, and then we've got a reduction, and we could combine these into an inner product, where the way this works then is if we go up to over here, we say 0 equals this one, different from 0 equals this one, different from 0 equals this one. And so on. And then we go through the whole array like this. It's slightly faster, I think, or at least it can be slightly faster, because it allows the interpreter to know everything that's going on. It doesn't actually need to look at first a comparison and then do the XOR. It could do that whole in one go if it understands how to optimize that. So this is a quite nice way of expressing it. But we also have a built-in way of doing this. There is a function, system function called quaddt for datetime, and quaddt is normally used to convert between various formats. However, there's a special, and it uses these format codes on the left. There's a special format code which is 0, which doesn't convert to any particular format. Instead, it asks whether this is a valid date. It's a datetime validator. So all we need to do here to test whether a date is valid is to, so to say, convert to format 0, and a normal timestamp with year, month, day, that is format number -1. So that means if then we need to make sure to enclose the argument, so that it's a one vector is one element. So then we can, for example, say, is the 30th month and the 100th day in that 30th month, is that a valid date? Of course it isn't. Is the January 1st, is that valid? Yes, it is. And what about February 29? That's the one day that determines if it exists. Then it's a leap year. If it doesn't exist, then it's not a leap year. So in 1900, that didn't exist. But what about in 1904? Then it did exist. So all we need to do when we have an array of years is to add 229 to each one of them to make it a full date. And then we ask quaddt whether that's a valid date by converting, so to say, to format number 0, which is just validation. If we go and take our array over here, then we can start making a function for this. Let's forget this part for now. We want to concatenate with a constant right argument to concatenation, and we want to do that on each one. So this gives us a matrix of these 4 vectors. And then we just need to say to quad_dt, which already handles arrays, we want to convert from the normal timestamp format to validation numbers on all of these, and that gives us our result from before. So that's like a very neat way to write that as well. And that this works on anything, and including on a single number because of the each. So it will go into, so to say, this scalar, and then the result will still be a scalar, and we have that enclosure that we needed above. So I'm going to see that this works as well. Thank you for watching.